So, welcome to Lecture 5. So far, what we've been doing in the class is representing stuff and manipulating stuff. And that was really the focus of all of our work on computational Boolean algebra. And so, in the previous week, we built and explored some powerful methods, binary decision diagrams, SAT solvers, to be able to do this. But now we actually want to move on and design stuff. We actually want to synthesize stuff. And so, the first thing to look at is two-level logic. And so that's a standard sum of products form, a lot of AND gates and an OR gate, and it turns out that there are some powerful synthesis techniques that we can use that are going to make use of all of the great computational Boolean algebra that we started with. So in this introduction lecture, where we just look at the basics, we're going to review basically the structure of two-level forms, the structure of optimal solutions to two-level forms, and introduce an idea that maybe we can solve this with a heuristic method, and not exactly, so that we can actually tackle big problems. So let's go look at that.
To date, we've been talking about computational Boolean algebra for representing things, for manipulating things, and one of the great applications was for verifying things. For example, our two blocks of logic implementing the same combinational function. This is all good stuff, but to move forward, we need to move from representation to synthesis. How do you actually design something? How do you optimize a design so that it has a minimum amount of hardware? And the first place to start for that is classical two-level logic. So let's go take a look at what those problems look like. This, I hope, looks pretty familiar. Two-level minimization means we're trying to find minimal sum of products forms where we have many AND gates, each making a product term, and a single OR gate summing them all together. So this is, SOP logic, as you probably saw some point in your, your basic, introductory digital design classes. What is our goal for minimization here? Well, it means that we want the fewest AND gates, and so I'm showing you all the AND gates here. We want the fewest AND gates in the design, and among all such designs that have the same number of AND gates, we would like the one with the fewest input wires. And there's a name for those input wires. They're called literals. It's the appearance of a single variable in true or complemented form in an input to an AND gate. So I give you this little Boolean function below. F is AB bar plus AB bar C plus ABC plus BCD plus BCD bar. And then I've drawn it below as a logic network. There's 5 AND gates. 1, 2, 3, 4, 5 of them. The first one has AB bar as the input, then AB bar C as an input, ABC as an input, BCD as an input, BCD bar as an input. And if I'm going to ask you, so how many literals are in this design, just pretend you drew it and count the wires. That's all this means. So how many literals are there? Let's just count the wires. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 literals in this design. And the reason this is worthwhile knowing is that this is actually a pretty good metric for success. Let's try to minimize the number of literals. If we can minimize the number of literals, we're probably going to do a pretty good job in getting a minimum design. Now, the problem is that none of the methods is really effective or practical here. You know a lot of Boolean algebra. Boy, that's really hard with a lot of variables. It's hard enough with a half a dozen variables, let alone 40 variables. You can't tell when you have a good solution when you do these things by hand. Carnot maps are the same problems, hard with many variables. You can do 6 variables. If you're awfully persistent, you could do 7 or 8, but boy, you still can't tell when you're done. You can't do 20 variables. And there are tabular solution techniques, famous things like Quine-McCluskey. They have an unfortunate problem, which is they're intrinsically exponential. So you can get a good result, you just can't afford it. We need a better strategy. We really need a very different idea here. And there are 2 big ideas that we're going to see in this lecture. The first big idea is that we are just going to stop trying for the best and the perfect answer. This is just going to go away. We're going to try to get a good answer. We're going to actually get a very good answer. We just can't guarantee it's the perfect answer. And the second is iterative improvement. And what that means is that we're going to take an answer, and then we're going to do something very interesting to that answer. We're going to reshape it in a way that allows us to produce another answer, possibly a better one, and we're just going to keep iterating that until basically it doesn't get any better. That's certainly very different than the way you've seen Boolean algebra for things like minimization so far. So let's just go look at what that might involve. So here's an example of the difference between best and good enough. And on the left, I've got a Carnot map, a classical 2x2 Carnot map, AB on the horizontal axis, CD on the vertical axis. It's got 4 cubes, which is to say 4 product terms that we've got covered. It's got an AC bar term, which is clearly the 2x2 cover in the upper left. It's got an AD term, which is the rightmost two columns and the middlemost two rows. And then it's got a CD bar term, which is the entire bottom row. That's really the best you can do. I mean, there's just no better answer to this problem. The solution on the right is a pretty good answer. It retains the AC bar cube, top left 2 by 2. It retains the CD bar cube, bottom row, but it replaces the AD cube with two cubes that actually overlap some other stuff. So there's now a C bar D cube, which is the whole second row of the Carnot map, and there's a new AC cube, which is the bottom right 2 by 2 corner of the Carnot map. And if you were to compare these two solutions, what would you notice? Well, they're both made of product terms, which we now know we can call cubes, that are as big as possible. And that is to say, I cannot take any of these things that I've circled in the Carnot map and I cannot make them bigger. We insist on this. These things in this form are called prime implicants. So roughly speaking, an implicant is anything you can circle in a Carnot map, and a prime implicant is a product, also a cube, that's as big as possible. I can't make it any bigger. And there's a very, very famous result from the 1950s that says the best solution is always composed of a cover of primes, which is to say a bunch of things you can circle on a Carnot map that are each as big as they can possibly be. Okay, so but what's going on with that solution on the right? It's actually got some subtle stuff that's worth talking about. So I'm again drawing the same best solution on the left at the top of this slide, and I'm again showing the same good solution. There are a couple of things that I can say. The first thing that I can say, as I said on the previous slide, is it's made of primes. Every cover, every cube is as big as it can be. But neither solution can be improved by removing anything. And clearly on the left, every one is covered by exactly one prime implicant, so I can't do anything. On the right, it is not the case that every one is covered by a single cube. However, I can't take any single one of those cubes away without uncovering something, right? And so there's a technical term for those things. Both of those solutions are irredundant, which is to say they are not redundant, which is to say I cannot point at any single cube and say, you there, go away, I don't need you. Now, this is also an important thing that we're going to strive for in the solutions we seek. We're going to look for solutions that are prime, each of the cubes is as big as they can be, and irredundant, we don't have any extra ones. But this is actually kind of interesting because it really suggests something a little deeper. So imagine that you could have a little graph over here, and this is all conceptual, and on the horizontal axis is every single solution, which is these circles in the Carnot map that I'm illustrating here. I can't really do this, but just conceptually. And then on the vertical axis, let's pretend that we could measure the cost of each one of these. We actually can. If we counted something like literals, that would actually be a pretty good model of the cost. And we'd see what turns out to be a really interesting, kind of a bumpy kind of a cost surface there. The point of the best solution is that it really is the one with the deepest minimum. That's the best solution right there. I can't do any better than that. I don't care where you look. That's the best I can do. The point of the good solution is that it's also a minimum. It is just not the best one, right? So the best solution is a global sort of a minimum. The good solution is a local sort of a minimum. And what local means in this case is there's nothing simple that I can do to this design to make it better. I can't just take one of those cubes and make it bigger. Sorry, they're already prime. They're as big as they can be. I cannot take any of those cubes and get rid of them. Sorry, this is irredundant. Wow, this looks tough. I need a different idea. In fact, I need a very different idea. And that's where all of the really interesting stuff in our lecture about two-level synthesis starts. So let's start by looking at what those very different ideas are.